Okay, so once more. Frying jalapenos, chopping them up fine, frying a panful. Okay? The finer I chop them, you think, the quicker they'll fry. Okay? And we want a graph of the mass of the average piece in milligrams, which is easier to measure than the dimensions of the pieces because they're all irregular, right? And the time to fry a panful. Okay? And I asked you to draw the graph. And most of the class drew a straight line. A couple of people drew a line that was concave up. Somebody drew one down below the axis, but of course it doesn't take a negative time. So you might want to flip that and then you'd end up with this. Okay? Make sense? Okay, so good intuition. You understand that it's going to take longer if the pieces on the average are bigger. Okay? And that's all I was really looking for. We're not going to get into the details of why it might be concave up or concave down or straight. Okay? Now we could do the physics of that. Do you want it? You want me to analyze the physics of it for you? Take about a month. Learn a lot of physics, heat transfer and material properties. Yeah, it'd be interesting, but we can't do that. Okay. Plus, I'd have to do a lot of experiments, but this is plant tissue. That's biological as well as physical. Things I don't know. And things I pretend I don't know. Okay? Now, okay, so, let's assume that the graph looks like this. Now, what functions do we have that might look like this?
X squared.
Sorry?
X squared.
X squared could look like that. What else? X cubed could look like that. I mean, your domain, of course. What's the domain of this function?
Zero to infinity.
The mass of the average piece in milligrams, right? What kind of numbers do you get for the, if you weigh the average piece? Get any negative numbers?
Always
Negative mass? Okay, good. You know, antimatter is hard to deal with. Okay, you know, tends to blow everything up. Okay, I mean for blocks or miles or whatever. Okay. Okay. So what are, you can't have negative numbers. Are there any other numbers you can't have for the mass of a piece? You ever seen anything with a mass of 0?
Mm-hmm.
No, if it's got a mass of 0, it ain't. Doesn't exist. Okay? I mean, photons, yeah, but we're talking about matter. If it's matter, it's got mass. Okay? So, if it's concave up, it could be x squared. You know, the shape of the x squared, you'd have to scale it differently. Could be an x squared. What else? It could be an x cubed, because that has the same basic shape. What else has this basic shape? Could it be 2 to the x? Yeah, now what's the difference between 2 to the x and x squared or x cubed? How can you tell the difference? Well, x squared and x cubed, as you approach 0 here, approach 0 here. They approach the origin, right? Whereas 2 to the x goes through the point 0, 1. So it goes through a point above the axis, right? Now, if you include the time it takes to heat the oil up, it takes a little time for it to start frying, okay? then, you might have an automatic time interval. So you'd have to be up here on the axis someplace before you could start, right? Now, if you say, well, let's heat the oil first and then do it, okay? There'd still be a delay, but you can worry about things like that. So, when you're trying to apply these functions in the real world, you got to think about those things. What's the range? Okay? If the range is from 0 to infinity, that could be like x squared or x cubed. If there's a delay, then it's from whatever that delay is to infinity, right? But it could still be that you have an x squared that you just raised by a little bit. You did that for homework. It's one of the reasons you want to think about transforming a function by raising all the points up. Okay? Does that make sense? The more you've done, the more sense that should make. If you haven't done those exercises, I think most people have, but if you haven't done those exercises, you didn't understand what I just said. Okay? That's why you do the homework. So, okay. So, anyhow, little side note on domains and ranges. There are factors that could make the range that. If the pieces are big enough, it'll take forever. Or if you're frying them at too low a temperature, they're never going to fry. So you can keep them on there forever. Although you probably don't, your pan probably won't last that long. Neither will you. Okay. So, practically, it really wouldn't go to infinity. Practically from 0 to a lifetime. If you're the one frying. Okay, so domain and range are important. Now what I really want to focus on though is, what's the meaning now of slope and the run and the rise of this fundamental triangle? Because I really want you to be able to interpret a fundamental triangle. Many of you will have a calculus course in your future. If you know how to interpret a fundamental triangle, it'll be very helpful to you for understanding what calculus is about. You'll learn more. You'll have more options in your education and in your profession. Plus, it feels kind of good to understand something with a little bit of substance to it. Okay? Okay, so what's the meaning? Well, what's the meaning of the run? Now, this is how you analyze a fundamental triangle. Notice I don't have any numbers in this, because if I ask you what the run is and I have numbers on it, you're going to give me a number instead of a meaning. Okay? We want to know, for this type of graph, what the rise and the run means so we can figure out what the slope means. Okay? So, the run is what? The rise is what? So slope is what?
I love being an engineer.
Well, what's the x-coordinate of this point mean? What's the meaning of your x-axis?
The mass of the average piece.
The what?
The mass.
The mass. Okay? The mass of the average piece. Okay? And what's the x-coordinate of this? Yeah, it's a mass of a piece. If I don't chop it, it's fine, right? Okay, so here I'm chopping finer, here I'm not chopping coarser. And you expect if I chop them coarser, that's why you made the graph upward, okay? I made a rising graph. So you knew that, but you gotta know how to put it into words and into meanings, okay? So, what does the run mean? Well, how do you get the run?
The change of x.
Sorry?
The change of x.
Yeah, it's the change in your x coordinate, okay? Well, that's not a bad thing to start with. It's always the same. Whatever the run is, it's a change in the x coordinate. Now we've got to put a meaning on that, but it's very helpful to just say what it is. So what is it? The x-coordinate is the average mass, right? Mass of the average piece. So I just draw a change in mass of the average piece. Now, that doesn't change when I'm frying a batch. You know, I chop it up, get the mass of the average piece. I just count the pieces as I chop them, right? And then weigh them all and divide by how many are. Okay. It's a little hard. You have to chop kind of slow to keep counting. You don't want to chop too many at a time, you lose track. Okay? And if you're chopping fast, you're not going to do that. But you can do a sample or something. Okay? Take a little blob, typical, you know, mix it all up, take a little blob and, you know, count the number of pieces and weigh it. You get a pretty good indication. So, change in the mass of the average piece between two different trials, right? So we chop to this mass and we chop to this mass and we see how long it takes. Okay, that gives us 2 points in the graph. Okay, if we got a nice curve, then we can kind of extrapolate to other sizes. Okay, so change in mass of an average piece. Between two trials, okay? The rise is what? Well, you start out by it's the change in the y value, right? Between the two trials. It's a change in the frying time. Trials. Okay? So what's the slope? Well, literally, change in y divided by a change in x, right? Change in what? What's y?
Time.
Oh, y is the frying time, right? Or time to fry, you know, however you want to say it. Just say it in a way that's unambiguous, but either of those would be good. So change in, and I'm using frying time. divided by change in x. It's rise over run. And I probably should say it's rise divided by run, or change in y divided by change in x, or change in the frying time divided by change in the average mass of the piece, okay? So it's a change in average mass of the piece. And you want to write enough words that you can look at it and not have to look someplace else and remember what that means. Because as you're reasoning through this, especially when it's foggy, which it will be, I mean, these things get foggy real easy, okay? There are things that I got to think quite a bit on, you know, some things deeper in physics, you know, and got to really work to get a handle on what that thing means, because it's pretty abstract, okay? Right now, everything's abstract to most of you. This is new, okay? So you got to spend some time on it. The fog will clear, because the order of what you do is always the same. It's just that the words change, and then you got to think about what the words mean. And I'm not going to ask you anything about quantum computing, okay? Not going to ask anything about quantum mechanics and cosmology, okay? Unless it's really simple. Just want you to get the process down so you can think about some basic things and understand why this is important. Okay, so change in frying time divided by change in the average mass of a piece. Watch that word. That word is respect. With respect to, I'll write it up here again. I'll say it out. With respect to average mass of a piece. Now, practically, why is that important? Well, I'm standing there, and the wind keeps shifting so that this stuff keeps blowing in my face, and I'm saying, gee, I wish this was frying a little faster. Or maybe I have to be someplace and say, no, I'm not going to make it. This is not going to fry. Now I'm going to have a bad batch. Okay? I'm out of time, and it's not done. So if I know this and have a feel for how fine to chop it to get the thing fried in 20 minutes, and have some data, and you know, or if I'm in a food production industry, and to manage the workflow in my food production factory, I've got to know precisely what to expect. Okay? So I set my machinery, because I usually go to have machinery to do the chopping. Okay? Only people that really like knives do the chopping themselves. Okay? I like chopping with sharp knives. You understand how a curve like this could be useful. Okay? So I can ask myself now, well, if it's taken me this long to fry it, pieces of this size, about how many pieces do I need? Or, you know, just using the slope of this thing, I can estimate, if, okay, let's just say that, okay, at this mass, it's requiring 21 minutes to fry, and I want to do it in 20. Okay? Well, I could kind of follow this slope rather than having to figure out anything about the curve to estimate how much finer I need to chop the things. And that might be a good enough estimate to get me within a few seconds of 20 minutes, and that might be good enough. Okay? So there are all kinds of applications for something, for the idea of a slope. To understand the slope, you have to understand the rise and the run, and you have to be able to do this interpretation. Again, slope is related to derivative in calculus. If you have calculus class derivatives, one of the 2 or 3 most important mathematical concepts that's ever been thought of. Okay? Very important. And very important for business, very important for almost all the sciences. Okay.